I wish to thank the organizers, Michał and Johannes, for having this nice conference. So I came rolling today into the university after that dinner yesterday. That's amazing. I also want to thank them for the opportunity to present my work here. And I must admit that actually, so this talk is a bit off topic in the sense that there is no atom, so it's only about ions, so it's a pure ion system. But to remedy this a bit, it will be about lattice gauge theories, and lattice gauge theories are kind of hybrid theories. You have the matter fermions and the gauge bosons, and maybe in the future one can really make use of these atom-ion hybrid systems to build even better quantum simulators of lattice gauge theories. But yeah, that's something for the future. Today I will really speak about only trapped ions, a quantum simulator of spin systems. And well, if you think of spin systems, this kind of Hamiltonian may come to your mind. So this is of course the famous Ising model, which has been realized in trapped ion quantum simulators. Or well, if you're a little bit more quantum minded, you may think of a Hamiltonian like that. This is the XX model. But the type of Hamiltonian which I'm going to promote today looks a little bit different. It has this spin, spin, spin interactions. And so what I want to show you is, first of all, how can we get to such a Hamiltonian with trapped ions? And before that, I want to argue why actually we are interested in this type of Hamiltonian. And I already mentioned, so the interest into this Hamiltonian comes from lattice gauge theories. We can use this to build quantum simulators of lattice gauge theories, and lattice gauge theories are really very universal theories in nature. Of course, they originate from the high energy physics, quantum chromodynamics, but they also find a lot of application in the field of condensed matter, in the low energy sector for spin eyes, frustrated spin systems, or also topological spin models like the toric code, which are of course extremely relevant in the context of quantum error correction, quantum computing. So lattice gauge theories are interesting, but they are also very hard to solve in general. So classical computers have problems in simulating this, and this is the reason why we would like to have quantum simulators of lattice gauge theories. And well, there has been a lot of progress in the past years already. So in the field of cold atoms, Rydberg atoms, and actually it started with an experiment here with trapped ions in 2016 in Innsbruck. So you may wonder if, why do I propose another quantum simulator to study lattice gauge theories if we already have so many? So one of the reasons which I may put here is the following. So in this experiment with trapped ions, for instance, the situation is like that. So you have a lattice gauge theory. This means you have fermions and bosons, gauge bosons, and they are connected through local symmetries. The Gauss law, which then can be used actually to integrate out one of these species. You can get then an effective theory only of fermions or only of bosons, and this has been used in this experiment. So this is, of course, absolutely fine. You can do that, but you have a quantum simulator, and one of the main things in quantum simulation is the verification of the result of a quantum simulator. And if you want to, if you have a lattice gauge theory, you can always use this Gauss law to verify your device. You can look if the Gauss law is still obeyed, and then this gives you a way of detecting errors in the quantum simulation. But if you have used the Gauss law a priori to build your device, then you don't have this verification opportunity left. So this is why we would like to have a quantum simulator which does not integrate out, which keeps all the degrees of freedoms intact. And this is what I'm going to propose. The concrete theory which we want to study is a type of Schwinger model, so a model for quantum electrodynamics. In this model, you have the fermions, so staggered fermions, electron, positron on alternating matter sides, and in between, on the links between the matter sides, there are the gauge fields, the electric fields. And so this is how this Hamiltonian for the Schwinger model looks like. The interesting part is this here, where you have the creation or annihilation of a matter pair and then the gauge field in between. This theory has the Gauss law. Has this local symmetry, which is very well known from electrodynamics. So it's really just the original Gauss law, the divergence of the electric field is related to the local charges. So this is then, I mean, represented by this operator, and all the physical states have to annihilate, have to be annihilated by this Gauss law operator. So this is the local symmetry which we have in this model. And now to do a quantum simulation of this Schwinger model, the typical way to do it is to replace the gauge, the matter fermions by spin variables. So this is just a Jordan-Wigner transformation. So this is like you can really map one-to-one from the gauge, from the matter fermions to the spin 1/2 objects. And then a modification of the Schwinger model is done with respect to these electric fields. They are also replaced by spin variables. And then, I mean, you have modified the theory. It's not the Schwinger model anymore. It's then called the quantum link model, but it has similarities to the Schwinger model. And if you take a representation of spin which is infinite, then it would really be, again, a one-to-one mapping. The interesting phenomenology which we find in this quantum link model is, for instance, pair production. So you have a state here where you have one electron and one positron here, and then there's this electric field line between these charges. So this then is represented by a spin configuration like this. And you find then if you subject such a state to this quantum link model, it performs the dynamics in which at some point you have a state like this, where an electron-hole pair has appeared here in between, and the electric fields have been changed accordingly. So this is pair production. There is another very interesting phenomenon in these lattice gauge theories in the quantum link model, namely there is weak ergodicity breaking. So you have certain states, you find that there are certain states which do not thermalize or thermalize only very slowly, so-called quantum many-body scar states. So this is shown here. So a generic quantum state like the green one would thermalize very fast. And if you look at the time evolution of some observables, and whereas these quantum scar states, they have these long time oscillations. And then there is, of course, the question, how can we identify, how can we find quantum many-body scar states in the spectrum of the system? And so here is shown the entanglement entropy as a function of energy of this quantum link model. And then you see there, there are a couple of low there are a couple of states which have low entanglement entropy, so these red ones, in which are equidistantly spaced in energy. And these states, for instance, turn out to span this non-thermalizing manifold, and maybe there are more of them, so it's really an open question of how to find this ergodicity breaking manifold in this type of systems. And yeah, so these are some of the reasons why it would be interesting to study this type of theories. And now, yeah, here is the Hamiltonian again for the quantum link model. And now, if you take these spin variables which correspond to the fermions, and you make a spin rotation, and if you also then replace this gauge boson spin by spin 1/2 object, then you end up with this Hamiltonian, which I have shown you in the beginning. So this Hamiltonian is really a quantum link model. So this is why it would be nice to have a quantum simulator of this Hamiltonian. And now I will show you how we can actually get there with trapped ions. So, and the way is very simple. So we just take the Molmer-Sorensen scheme, which I assume most of you know very well, and modify it a little bit. So in the Molmer-Sorensen scheme, we have two couplings, red and the blue sideband coupling. And now what we do, we take one of these couplings here, in this case the blue one, to be not of the first sideband but of the second one. So what's shown here is the different spin levels of three spins, and then this and the dashed lines are the phonons above these spin levels. And now you see that this blue coupling it creates two phonons, whereas the red coupling removes one phonon. So we have a red first sideband and a blue second sideband transition, and both are, of course, a little bit detuned with these energies actually written here. So and now it does not require a high level of mass to realize that if you take a third order process where one of these blue processes happens and two of the red ones, then we exactly hit a resonance where 3 spins are flipped, and this is exactly the type of process which we want to get. So this is the way how we get the 3-body interactions. Now, we are not completely done yet because unfortunately there are also second order resonances, for instance, processes like that, and they produce 2-body interactions. And in fact, you can easily distinguish these two processes if you just look at the dynamics of the system for different initial states. So here we take an initial state which is spin polarized, and then we only get the 3-body Rabi oscillation. So this is the dynamics which we want to have. But if you take a different initial state like that, there's also dynamics, and it's much faster, and this is generated by the 2-body interactions. So the good thing is now, if you look at how these interactions scale, so the 2-body interactions scale with 1 over the detuning, whereas the 3-body interactions scale with 1 over detuning squared. So this means that if you just take this laser scheme twice with opposite detunings, then the 2-body part will cancel, whereas the 3-body interactions get constructively enhanced. And that indeed, I mean, one can check again. So this was the situation we had before. And now if you have this doubled scheme, you see the 3-body oscillations go twice as fast, whereas the 2-body interactions have basically disappeared. And yeah, so this is mainly how it works. So of course, the situation is a little bit more complicated. There are multiple modes in the system, so we have to check different and do some fine tuning with the trap frequencies to make the phonon spectrum very largely spaced, but I mean, with certain amount of fine-tuning, you can actually get the situation which looks very promising. So yeah, that is how it works. So with a generalized Molmer-Sorensen scheme, and yeah, with that, I'm finished. So I would like to thank my collaborators in this project, which are Barbara, a PhD student at ICFO. Sorry, she's a high energy physicist at the University of Maryland. Mohammed Hafezi, he's also at the University of Maryland, quantum optics physicist. Guido Pagano is the experimentalist in this group. He is at RISE, and he really wants to realize this in the lab. Ali Reza is a PhD, or was a PhD student of Mohammed. Yeah, and thank you for your attention. Thank you.
Questions for Tobias?
So can you elaborate a little bit on fine-tuning of the phonon structure in the
Yeah, so this, so I mean, so one of the main problems is that, I mean, so this simulation actually here, it was a simulation which we have done only with one center, only taking into account the center of mass phonon. So here, I mean, it really works very nice. But then if you consider that there are more than the center of mass modes, then of course this cancellation of the 2-body interaction does not really work perfectly, because I mean it assumes it works with respect to one mode, because there is symmetry with respect to this mode, but with respect to the other modes there is no symmetry. Then I mean the detuning is different for the two different beams, so there is no perfect cancellation anymore. And therefore, I mean, you really have to suppress the effect of the other modes. And that can be done by basically, squeezing the trap frequency such that the phonon spectrum becomes more, so that the distance between the phonon modes becomes larger. So you see, so these, if you compare these two figures here, for instance, this is for a trap, longitudinal trap frequency 1 megahertz. So you get this type, I mean, the 2-body interaction is stronger in that case than it's here, where we just have taken a trap frequency which is 1.5 megahertz. So you have to make this longitudinal trap frequency as large as possible. And of course, I mean, you cannot make it infinitely large, because then you enter this zigzag deformation. But yeah, that is basically one of the things which have to be done to make this work best. And yeah. So I mean, we have made the full simulation for the spin boson model, yeah. So 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 the can you repeat, please? So yeah. Okay. Yeah. I mean, so no, there is no star shift. I mean, the star shift also cancels. If there, I mean, the star shift means like you had a effective magnetic field term in your Hamiltonian, and that would not that would modify this. I mean, so I mean. In this case, maybe there is, so typically, I mean, what I think kind of quantifies the amount of star shift is if you look at these three-body Rabi oscillations, so they should go from -1 to 1, yeah? And if they don't go to 1, then there is star shift. So here there is some star shift, but in this case, I mean, it's not very much. So and I mean but that depends mostly, I think, on the choice of the detuning and I mean, of course, you cannot make the detuning infinitely small, so you have to be sufficiently detuned to avoid that.
Great. Well, let's do this again. And we're going to move on. We're our last of the theory session here.